Okay, so differentiation by first principles is mentioned on the paper 2 pre-release, not the paper 1, but I'm going to do a video on it now anyway. So this is the formula we find on the formula sheet. I'm not going to go through the derivation of it. You can sort of look that up in your notes if you want, but I'm going to just use it to prove what the differential of x cubed is. And of course, you know, we sometimes get functions described like this or like this, and you know, the differential dy by dx f dash of x, these two things are interchangeable, so don't stress about which one you need to use. They're completely interchangeable. So just using this notation here, this is my function. So what this means is what happens when you make x equal to x plus h. So that gives me x plus h cubed, take away x cubed over h. And I'm going to expand this. I've already done it. You could pause the video, I suppose, at this point if you wanted to. That gives me x cubed plus 3x squared h plus 3x h squared plus h cubed. Take away x cubed, all divided by h, so that the x cubes disappear. So that gives me 3 Now I can cancel out the h because everything's got an h in it. Okay, so I can divide by h, so that cancels out that. H squared just becomes h, and h cubed becomes h squared. And we now ask, what's the limit of this as h becomes very small? Well, as h becomes very small, that will become almost 0, so 3x times 0, that becomes 0, that will become 0, so I'm just left with 3x squared. And of course I know that's what you get when you differentiate x cubed. So, you know, I've proved, using first principles, that's what I knew. Okay, so the specification mentions small integer powers of x, so we've done x cubed, might get x squared, but then the other two are sine x and cos x. So and we did this recently, so why don't you have a pause and have a go. So I've done sine x, so using the formula on the formula sheet, it's f of x plus h take away f of x over h, and I've used the cos a plus b formula to expand that. And then at that point I used a small angle approximation, so I replaced cos h with 1 minus h squared over 2. That's the small angle approximation on the formula sheet. I replaced sine h with h. I then multiplied that bracket out, so sine x times 1 gave me a sine x, and sine x times minus h squared over 2 gave me minus sine x times h squared over 2. But then that sine x cancels out the sine x that's at the end there, so they're gone. And then I can divide everything that's left by h. So I get minus sine x times h over 2 plus cos x. And the limit as h tends to 0, well, that term will become 0 because it's sine x times 0. So you're just left with cos x, which is what we were expecting. Okay, I'll pause again and have a go at cos x, very similar. Okay, so that's just plugging in the formula from the formula sheet, and then I used cos a plus b, remembering when it's cos a plus b, you've got a minus there. Sorry, I didn't really leave myself enough room for me to divide by h, but it's all divided by h. Then small angle approximation, so I replaced cos h with 1 minus h squared over 2, and sine h with just h. Then multiplied out that bracket, so you've got cos x minus cos x times h squared over 2, minus sine x of 8, and sorry, that's, I perhaps ought to be in brackets, that's h times the sine of x. So the cos x's cancel out. I've then got an h in everything that's left, so I can divide everything by h, this term becomes 0, so you're left with minus sine x, which is what we were expecting. It is definitely worth practicing those two, but that's paper 2, remember, paper 2.